November 8, 1944. Admiralty Research Laboratory, Teddington, England. Dr. James Whitmore places a sample of Type 7 U-boat pressure hull steel under the tensile testing machine. The metal specimen is 2 inches long, ½ inch wide, precisely machined from the hull of U-534, a German submarine recovered intact after scuttling in shallow Danish waters 3 weeks ago. The U-boat was found resting on the seabed at a depth of only 40 feet. Crew escaped. Hatches open. Seacocks opened deliberately to prevent capture. British salvage teams raised it, pumped it out, towed it to England. Now pieces of it are in Whitmore's laboratory being tested to destruction. Intelligence reports claim Type 7 U-boats can dive safely to 200 meters. German technical manuals captured in France specify hull steel with tensile strength sufficient to withstand pressure at that depth. The steel Whitmore is testing should easily meet those specifications, should withstand the crushing force of water at 200 meters depth, should perform as designed. Whitmore starts the test. The machine grips both ends of the steel specimen, begins pulling, applying force, measuring how much stress the metal can withstand before it fails. The numbers appear on the gauge, climbing steadily. The steel resists. Then suddenly, at a stress level equivalent to water pressure at 140 meters depth, the specimen snaps. Clean fracture, brittle failure, no warning, no gradual deformation, just sudden, catastrophic failure. Whitmore stares at the broken pieces. This should not be possible. German metallurgy is supposed to be excellent, among the best in the world. The steel should have failed at 200 meters equivalent pressure, not 140. He runs the test again with a different specimen from the same U-boat. Same result. Failure at 140 meters equivalent. A third specimen. Same failure point. The pattern is consistent and impossible to ignore. The steel is failing at pressures far below its rated capacity. Something is fundamentally wrong with U-boat hull steel. This discovery will explain one of the great mysteries of the Battle of the Atlantic. Why so many U-boats simply vanished without a trace. No wreckage, no survivors, no evidence of attack, just gone, disappeared in deep water. Naval intelligence has been tracking these disappearances since 1941. The numbers are significant. Out of 783 U-boats lost during the war, approximately 200 vanished in circumstances suggesting possible structural failure rather than enemy action. Submarines that radioed their position then went silent. Boats operating in areas with no reported Allied activity. Losses in deep Atlantic waters where recovery and investigation are impossible. The official German explanation has always been enemy action, depth charges, air attacks, mines. But the locations and circumstances of many disappearances do not support this. British and American forces maintain detailed records of every U-boat attack. Positions, dates, times, weapons used, results. When analysts compare known attacks to U-boat losses, there is a gap. A significant number of boats lost with no corresponding Allied action in the area. No depth charge attacks, no aircraft sightings, no minefields, just boats that stopped transmitting and never came home. The assumption has been that these boats were destroyed by actions that went unrecorded, or hit mines that were not charted, or suffered mechanical failures. But Whitmore's test results suggest another possibility, a possibility more disturbing than enemy action. The boats were destroyed by their own hulls, by steel that could not withstand the pressure, by metal that failed catastrophically when the submarine dove too deep. The Type 7 U-boat was Germany's primary submarine design throughout the war. 709 were built between 1936 and 1945, more than any other submarine class in history. The design was proven, reliable, effective. The hull was a cylindrical pressure vessel made of welded steel plate 21 millimeters thick in the pressure hull section. The steel specification was ST52, a high-tensile structural steel widely used in German shipbuilding. According to German engineering documents, ST52 steel had a tensile strength of 520 megapascals, sufficient to withstand water pressure at depths exceeding 250 meters. The hull design included a safety factor. Test depth was rated at 200 meters. Crush depth, the theoretical maximum before catastrophic failure, was calculated at 280 meters. German submarine commanders knew these numbers, knew that diving below 200 meters was dangerous. Below 280 meters was suicide. The boat would implode. The pressure hull would collapse. Everyone inside would die instantly. But 200 meters was supposed to be safe, was supposed to be within design limits, was supposed to be survivable. Whitmore's test results indicated otherwise. The steel was failing at pressures equivalent to 140 meters. That meant the actual crush depth was not 280 meters. It was closer to 180 meters. The safety margin had disappeared. The submarines were operating with almost no buffer between test depth and catastrophic failure. Every time a U-boat dove to 190 meters to escape depth charges, it was gambling with steel that might fail without warning. Every deep dive was potentially the last. The crews had no way of knowing. The steel looked normal, performed normally under most conditions, but under extreme pressure, deep underwater, it failed suddenly and completely. Whitmore needed to understand why. He began detailed metallurgical analysis of the U-534 hull samples. First step was examining the microstructure. He cut thin sections of the steel, polished them, etched them with acid to reveal the grain structure, examined them under high magnification. Normal steel has a relatively uniform grain structure. The individual crystals of iron and carbon are small and evenly distributed. Good steel has fine grains. Poor steel has coarse, irregular grains with inclusions and defects. The U-boat steel showed significant problems. The grain structure was coarse, irregular. There were large inclusions of slag and impurities. The metal had not been properly refined, had not been adequately processed. It looked like steel made in a hurry with inadequate quality control. Whitmore moved to chemical analysis. He needed to know the exact composition, what elements were present, in what quantities. Standard ST52 steel contains iron, carbon, manganese, silicon, and small amounts of other elements. The proportions matter. Too much carbon makes steel brittle. Too little manganese reduces strength. The balance must be precise. Whitmore used spectroscopic analysis to determine composition. The results were immediately concerning. The carbon content was slightly high, not dramatically, but enough to affect brittleness. The manganese was lower than specification. Silicon was within range. But there was another problem. The steel contained almost no molybdenum. ST52 specification called for small amounts of molybdenum, typically around 0.25%. Molybdenum is a critical alloying element in structural steel. It increases strength, improves toughness, prevents brittle fracture. The U-boat steel contained less than 0.05% molybdenum, 1/5 of the specified amount. This was not a minor deviation. This was a fundamental compositional defect. Whitmore understood immediately what he was seeing. Germinal was running out of molybdenum. The metal is relatively rare, mined primarily in a few locations worldwide. Before the war, Germany imported molybdenum from Norway, Canada, and the United States. When war started, those supply lines were cut. Germany had some domestic sources, small mines, limited production, not nearly enough for wartime demand. Molybdenum was needed for armor plate, for gun barrels, for aircraft engines, for dozens of critical applications. Submarine hull steel all show implosion damage. All were lost in deep water. All probably failed due to inadequate hull steel rather than direct depth charge hits. The wrecks are evidence, silent testimony, proof that the analysis was correct, proof that German submarine steel was fatally compromised, proof that hundreds of men died in boats that should never have been sent to sea. The evidence sits on the ocean floor, undisturbed, slowly corroding, but still telling the story, still showing what happens when you compromise materials in pressure vessels, still demonstrating that metallurgy matters, that chemistry matters, that molybdenum matters. The families of U-boat crews lost to possible hull failure never knew, never learned that their sons, husbands, fathers might have died from defective steel rather than enemy action. The German Navy never publicly acknowledged the problem. The information remained classified or obscure. When families received notification that their loved one's submarine was lost, the cause was listed as enemy action or unknown. The possibility that the hull failed was never mentioned. Some families might have preferred knowing, preferred understanding that their loved one died from equipment failure rather than in combat. Others might have found it worse, might have been angrier learning that the submarine was sent to sea with known material deficiencies, that Germany sacrificed submarine crews to steel shortages, that the deaths were preventable. The truth was kept secret. The families grieved without knowing. The pattern continues. Even now, 80 years later, descendants of U-boat crew members mostly do not know about the steel analysis, do not know about the molybdenum deficiency, do not know that their grandfather or great-uncle might have died from hull implosion rather than depth charge explosion. The knowledge remains buried in declassified reports and academic studies, available but not widely disseminated, known to historians and naval specialists, unknown to the general public, unknown to the families. The story of defective U-boat steel is important. Important for understanding how wars are won. Important for understanding the role of material science in military outcomes. Important for understanding that courage and skill are not enough when the equipment fails. Important for honoring the memory of submariners who died trusting machines that could not be trusted. But the story remains mostly untold, mostly forgotten, mostly unknown except to those who study such things. Dr. James Whitmore discovered it in November 1944. The discovery helped win the Battle of the Atlantic, helped save countless merchant sailors from U-boat torpedoes, helped ensure that Britain survived to see victory. But the discovery also meant that over 1,000 German submariners died from hull failures that might not have occurred if the steel had been adequate. Both things are true. Both matter. Both are part of the story. The story of how molybdenum deficiency killed German submarines. How one element, missing from steel in inadequate quantities, meant the difference between a pressure hull that worked and a pressure hull that failed catastrophically. How chemistry determined who lived and who died in the Battle of the Atlantic. How Dr. James Whitmore discovered it. How the discovery was exploited tactically. How German submarines dove into their own graves. How the steel betrayed the men who trusted it. How the war was won, in part through understanding metallurgy. That is the story that remains mostly untold. The story of the invisible killer, molybdenum deficiency, brittle steel, imploding submarines. The story that ended with hundreds of men at the bottom of the Atlantic, crushed by water pressure, their hulls could not resist, dying in machines their country knew were inadequate, but sent to sea anyway. That is what Dr. James Whitmore discovered when he tested steel from U-534. That is what his report meant. That is how material science changed the war. That is the story of the steel.